Here we are looking at a problem from the uniform circular motion unit, specifically a vertically aligned circle. That just means the object is rising and falling while it goes through its circular path. You can see that in the pictures. Some numerical information is provided. We are given the mass of the object. We are given the speed, 3 meters per second. We are given the length of the string as 1 meter. A couple things to point out before we start. Uniform circular motion infers a constant speed, so this ball will always be moving at 3 meters per second, no matter where it is in the circular path. Also, the length of the string is given as a length of 1 meter. If you look at the pictures, you can see that the length of string will also be the radius of the circle, so this 1 meter measurement will be for both length and radius. For any uniform circular motion problem, conceptually, we need to understand centripetal force, or the Fc variable. This is the net force for circular motion, so Fc will take the place of Fnet. And the rule is that this centripetal force is always directed towards the center of the circle. That's how an object turns. There needs to be more force towards the center than there is away from center. From there, let's look at some force diagrams. Starting at the top of the circular path, I can think of two forces that act on the ball at this location, a downward force of gravity from Earth and a downward tension force from the string, since the string is below the ball and pulling downward. I'll call this Ft subscript T, indicating the top of the path. Notice that both these forces point downward. More importantly, they both point to the center of the circular path. So we're going to add their effects together and set them equal to the centripetal net force. Both of these forces are responsible for helping the ball turn downward. Looking over at the bottom of the circular path, two similar forces, another downward force of gravity from Earth, and now an upward tension force from the string, since the string is above the ball and pulling upward. We'll use subscript B for this tension force for bottom of path, and because we want the net centripetal force to point inward, that would mean the force pointing inward, Ftb, must be greater in magnitude than the force pointing away from center, Fg. So my net centripetal force is large minus small, Ftb inward minus gravitational force outward. As we consider the question that we are being asked, another conceptual idea must be discussed. We're being asked where the string is more likely to snap. Would that be at the top of the path, the bottom of the path, or would it be equal at both locations? Conceptually, we want to know that the string is likeliest to snap when the tension in the string is the greatest value. So we should be solving for these variables Ftt and Ftb and comparing their magnitudes. Whichever has the largest magnitude will be the answer to this question. Here I'm just isolating the equation that we've already written for the ball when it's at the top of its path. In order to solve for the tension force at this location, I will need values for both Fc and Fg. So I'm going to go to the formula sheet and pick out a few equations that can help. For the Fg variable, I might use the weight equation. Remember that centripetal force is a net force, so I might start with Newton's second law, but recognize that this is a centripetal acceleration. It's about turning, and I'm going to have to sub in v squared over r for the a variable. So using those substitutions, another one for the AC variable, now establishing the given information in this problem, I have everything I need to solve for the tension force, and I get a value of 2.3 newtons when I do that algebra. Going to the bottom of the circle, very similar analysis, isolating the equation we've already written, using the same substitutions as we did previously, establishing the same given information as before, and now doing the algebra to solve for the tension at this location as 12.1 newtons. So clearly more tension at the bottom than we have at the top. The string then is likeliest to snap when the ball is at the bottom of its path. We're going to go with choice B here for this question. So to summarize, when you are solving questions from the uniform circular motion unit, I think one of the most important steps is to get these types of equations correct at the beginning of the problem. I call them Fc equations, or centripetal force equations. They represent the net force acting on the object, and they are not on your formula sheet. So they come from your knowledge of getting the force diagram right, and your knowledge of what centripetal force is. If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.